Hey, good morning, guys. Welcome back to another episode of Introduction to Computer Networks. This is Polly streaming live again from NTU. Yeah, good morning, Eslam, Lucas, Tasha, Noe, Qingyi, Yujie, Yongyi, Pinxiang, and Jiaxuan. Good. Now, greetings to all. There's one thing in the announcement I would like your attention to, which is point number 3 of week 3, episode 5 announcements. So next week's lecture, we'll be talking about how we send data securely over the internet. And there's a protocol for it. Okay. Now, in order for you to capture what I want to communicate in the videos next week, you might need to watch a playlist that talks about the public key crypto. It's a special system, public key. It's quite different from the traditional symmetric key system. Okay, so I have prepared a playlist, so there are a few videos that you can follow real quick to get a rough idea of the public key crypto. And that should help you understand the videos next week, the lectures next week. Now, today. Yeah, so today, we have more students popping in. Good morning, Yuling. Morning, Ali. Good morning, Ming Hong. I hope I pronounced the name right. And Zixuan. So today, there's going to be 4 groups of topic, depending on how much time we had. We will have. Yesterday I said that we have 3 groups of topic, but turned out that we only talk about 2 sets of topics. Okay, so similarly today, the plan was to talk about 4 groups of topics, but we'll see. First group is PS and the network structure. That's the parts that I planned to finish yesterday. And then the second group is called metrics. That's how we use to measure performance on the internet. So there are a few of these metrics we need to introduce there. And then the third group of topic is not technical at all. It's to talk about the internet service model. Okay, what that term meant is simply that we talk about internet protocols in layers, because there's a layered structure there. We organize the protocols, or aka the mechanisms. And the last group of topic is just that we want to, hopefully we will start chapter 2, okay, the application layer. And Cheng'en, double hi, back to you. And so back to group 1, packet switching. We know now packet switching and circuit switching very well. What we're doing at the end of yesterday is to talk a little bit deeper into packet switching, because hey, we mentioned that we send small packets, but how small? Can it be larger, or can it be very small, right? So yesterday we clarified, you don't want them to be large, okay, because otherwise when you retransmit, it's going to be a high overhead. Or the end-to-end delay can be much longer as opposed to if you send small packets. But you don't want to send packets too small, because in a packet there are 2 parts. There's the header part that has the control information. They are not the data you want to send. They are the information helping the router to decide what to do next. So the real data is in the payload part. For a small packet, the payload part is relatively small proportion of the whole packet, right? So the utilization of the network will be low if you send packets that are too small. So it's a little bit tricky deciding what is the right size for a packet. Today, we'll talk a little bit deeper into this notion, store and forward. Right? So we introduced this property and say that this is a property unique in packet switching. We don't have this in circuit switch network. So this video, okay, the first video today is to explain why it's necessary to do store and then forward in packet switch network. Sorry, push the wrong button. This video is the right one, store and forward. And why do we need to store packets first before forwarding it, right? This is one of the reasons that we still need to form packets. Why we cannot just streamline the bits. The reason has something to do with how the routers is working. So inside the router, there are 2 key functionalities, and there are 2 of these. First is routing. So there's some sort of algorithms there. The routers, given the graph of the network, computes the shortest route. At the end of it, we generate a routing table like this, a forwarding table like this. And the way we look up this table is by matching the destination address, okay, of the packet. And so if a packet comes into a router, inside the router takes the destination address in the packet and look up this table. If there's a matching entry, the router discover what is the next router to forward to, what is the right direction to pass this packet further. Okay, you see, router what? Oftentimes well connected to other routers on the internet. So this router here could have multiple ways of passing the packets further. Unlike the very simple scenario there, each router has only one outgoing link, right? So it's no longer that intuitive why packets need to be stored and then forward. Now you see, packets need to be stored here, and then the router can look up this field and match this entry and then discover, okay, this packet is supposed to go out on network interface 2, this direction, to this router next. Similarly, this router needs to store the packet entirely, and then it can look at the header, this particular field, destination address, and find out in its own routing table which router next to forward the packet. Yeah, it's exactly because of the forwarding functionality that's required to pass data around over a packet switch network like internet. So on packet switch network, we store packet before we forward it. So forwarding here is to move packets to routers all the way from the source, eventually reaching the destination. All right. We'll definitely tell you more as we come to chapter 5. Okay. So in datagram network or in data network, the way it works is let's receive a packet entirely, okay, and look up the destination address to determine which is the next hop. And so you see, if the routing table changed, if the graph changed, routing table would change. When the routing table changed, when the forwarding table changed, yeah, the subsequent packets might be following a slightly different path to the destination. Okay? So the routes, packet traverse might change in a session, in a data stream session. So the analogy here is that the packet switch network is a little bit more like the regular car network. Okay? If we are driving a car, a lot of times, hey, to find out the next segment, okay, which road segments we should go on, we might actually stop and pause and ask someone for this destination, for direction, or park to the side and then look up Google Map to find out which is the next segment. All right. So that was why we need to store and forward, because all the bits need to arrive in order for the router to see where the destination is and then decide what is the next hop to forward to. Unlike in circuit switch network, right? We set up a circuit and bits are just streamlined through the circuit. It's all hardware. But in a packet switch network, right? Well, packet is just sent, right? Who is there determining where the packet will go next? There's not a circuit at all. So there's a routing function, forwarding function implementing the router. In order for the router to decide which way to forward further, they need to check information in the packet. And some of you might be asking, hey, so all we need seems to be just the destination address, right? So if the destination address is early on in the packet, then hey, you don't have to store all the bits. You know what, you're right. But a lot of times when we send these packets, we also have this checksum bits, checksum sequence to ensure that there are no bit error in the packet. Okay, and in order to make sure that you pass the checksum, you need to receive the whole packet, because that checksum is computed out of all the contents of the packet. So if you want to check coherence, well, you need to take the whole packets before you can decide where to send the packet forward. Further, right? So that is why we need to store and forward. And you see towards the end that a packet switch network is also called a data network, because packets are essentially data. When internet was designed, it was designed to send data, not to send a voice call, unlike the telephone network that is based on the circuit switching principle. It is also called the datagram network, that is to contrast exactly in telephone network, if you send data, it's called a telegram. So in a data network, to send data, datagram. All right. Towards the end of the video, you also heard that sending these packets over the internet, they can be sending sequence, but arriving at the destination out of the sequence. So for certain applications who would really like the packets arriving in sequence, then you might want some sort of circuit-like behavior. And that is possible. One can actually emulate a circuit behavior in a datagram network, in a packet switch network, using some sort of tags, okay, special tags that allows the router to check quickly. So the next video explains the virtual circuit. Okay, it's not a real physical circuit as used in the circuit switch network. It's a virtual circuit that we implement in the packet switch network. Now, towards the end of this last video, you will see a taxonomy of circuit switch network, packet switch network, and different forms of implementing packet switch and circuit switch network. So, and actually in a packet switch network such as internet, we can potentially emulate a circuit-like behavior that is called virtual circuit network. So instead of looking at the destination field in the packet header, we look at a very special header field called the virtual circuit ID field. Okay, so there's a tag there, carries a number. Okay, that number determines which is the next hop. So inside a packet, there could be many fields in the packet header. One is called destination. There's another one called the virtual circuit ID. And one can look up that field and decide which is the next hop. And how do we do that? We'll talk about that also in chapter 4 and in chapter 5. And what's nice about this approach is that we can then try to ensure, okay, all the packets for that stream traverse a fixed path. In a way, packet number 1, 2, 3, 4, chances high that they arrive in order. In this case, in case routes might change, if the later route is shorter than the earlier route, chances there packet 1 might arrive after packet 2. So, packet switch network. To sum everything up, this is general communication network. Two different flavors depending on which philosophy we design the core of the network. If we are going for a circuit core, it's called circuit switch network. If you're going for a packet-centric core, packet switch network. In circuit switch network, we know there are different ways of dividing resources into pieces. Frequency division or time division. But either way, it's very regular following certain order. Things will need to be reserved. There's a call setup delay. It's good for long-lasting calls where you will prefer data not experiencing variation in delay, not experiencing losses. But this is very resource consuming. Each time we will not be able to allow many users going on at the same time. On the other hand, packet switch network, simpler, flexible, no idle resource, but we might have congestion. So that's this track, datagram network. We look to the destination network address and then decide which is the next hop to forward. And so we need to store the entire packet, and so they might get queued, and they might get dropped in case there's not enough space in the queue. But we can also try to emulate a circuit behavior using the virtual circuit tag, which allow us to look up into the packet header field that's a little bit faster and streamline the process more or less and maintain packet arrive orders. Packet switching versus circuit switching. All right, now the network structure. So it's going to come in two parts, two videos. The first part talks about how the internet evolves from the older times to like a decade ago. Okay, and you will see that it starts based on certain ration, but then it grows because there are some business opportunities and there are some also government policy involved. So this video, a little bit long, almost 5 minutes. Okay, see if you can stick to it to the end. Internet structure. It's a network of networks. Earlier we learned we have end systems at the edge of the internet. They're connected to the core through the access networks, which are part of these access ISPs. Now, some of these ISPs serve home users more. They're called the residential ISPs. Others serve companies and universities. They are more often being called institutions and ISPs. Well, either way, any two hosts in these ISPs wanting to send packets to each other, their access ISPs will need to be interconnected. As a result, we see a network of access networks. Over time, they grow pretty large and complex. And much of these growth is driven by the economics, and some of it driven by governmental or business policies. In the next few slides, what you'll be seeing is essentially the evolution of the internet. What I'm drawing here is a bunch of these access ISPs, or I call access nets here on this figure. Let me just omit drawing the end systems because there's just going to be too much of them and the picture gets too messy. So the first thing the internet engineers are thinking is this: how are we going to interconnect these guys? Well, one obvious way is, how about connecting them all? But as a result, you see there are n square connections. And when the internet grows, adding one more access net, we'll need to add n extra links. So this is going to be a very expensive thing to maintain. And so internet engineers go with the other extreme. Everyone connects to one global ISP in the middle. So data come here, and the global ISP transits the data for the access net to the destination. Similarly, here. So in a way, the global ISP in the middle here is providing transit services to the access nets, which are the customers. Now, as the internet grows, as the number of these access nets grow, then there'll be more paying for the transit services. Gradually, the global ISP will begin to see profit. And when business is profitable, you see competitors. So now we have not just one global ISP, but multiple global ISPs. So A, B, C here are 3 global ISPs. They're competitors, but unfortunately, they also need to collaborate. Because what? Just like the access nets needs to be interconnected so that they can serve the end systems, their customers. ISP ABC will also need to interconnect so that they serve their customers, the access nets. All right, so must interconnect. There are 2 ways for the global ISPs to interconnect. First is to establish peering links among each other. The other is to connect through these IXPs, Internet Exchange Points. Now these IXPs are special. They're typically set up by government fund or by the nonprofit organizations because it's kind of important that we have these, third company there maintaining the basic operation of the internet to avoid companies, commercial companies, to dominate. So that's pretty much the structure of the internet for a long time. But over time, we see more. So local communities such as this guy and this guy here can also grow. When there's enough number of these access nets around, we begin to see regional ISPs showed up. What these regional ISP is doing is this: offering lower price internet access to the access nets and try to negotiate internet access with the global ISP with a lower price. So hopefully the regional net here finds a margin of profit. So profit here and saving money here. For global ISP, this might not be a bad thing at all because it only needs to deal with one customer, which is the regional ISP, instead of multiple of them. Okay, so less overhead. Yeah, so you see, it starts by based on some ration, right? everyone connecting it to everyone, not sensible. But everyone connects to just one center ISP, core ISP, that is not exactly sensible either, right? That's a single point of failure. So yeah, governments would prefer, okay, not having an internet like that. So you gradually having a few major ISPs. And then the business opportunities for forming regional ISPs. Okay, so the beginning of the internet or early age of the internet is more more ration business opportunity and some sort of government policy to ensure that the internet belongs to everyone, okay, not being held by very few ISPs. Now, starting these recent decade, there's this special company, or many of the internet giants are actually also one of these companies. They own content. Okay, these are the content providers. What's very interesting about these content providers is that they don't really own the backbone infrastructure, internet infrastructure. They are not like the regional ISPs. They don't maintain cables underground. But they do have access to the access networks, which are really, really close to the end users. Okay, so these are the content providers. And these players join the internet. And so the structure of the internet is getting more and more interesting. Oh, I see many questions. So guys, let's play this next video and Polly will attend to the questions on the chat. So the modern day internet. And this structure has been there for a long time until about a decade ago. Content provider networks showed up. Let me talk about content provider network by example. So let me use Google here. It'll be easier for you to understand. So Google established these data centers worldwide. Okay. What they do is to go to access networks locally where the data centers are, and then ask to connect to the access network, their data center. Now, the number of machines they are maintaining there at their data center and the connections they are buying from the local ISP are actually comparable to the global ISP here. The entire infrastructure there at the content provider network is just as big as the global ISPs in the middle. But what's a bit odd is this. The content provider networks, they're actually physically at the lower level of the hierarchy. As opposed to the global ISPs, they are at the center of the hierarchy. Scale comparable, but where they are in the hierarchy, very different. All right. In the next picture, let me try to draw the network slightly differently so that you see where they are in terms of how resourceful these provider networks are. You see here then, the most resourceful one at the top, the least resourceful one at the bottom. So at the center, we have Tier 1 ISP and content provider network. Tier 1 ISP interconnect to each other through peering link, and they also connect to the IXPs. Content provider network somewhat different. They connect to the local access ISPs and IXP. All right. But keep in mind, this is not exactly absolute. Some Tier 1 ISPs might also have access ISPs connections. Google here, if this Tier 1 ISP offers a fair price, might also establish a connection. All right. Good. Now, the final slide is just to give you a rough idea what's inside a Tier 1 ISP. As I'm drawing here, it looks simple, but it's actually quite complicated. This is a Sprint's backbone. Sprint is one of the major operators in the US. It's also a Tier 1 ISP. Each of these red dots is called a POP, point of presence. So the row there is pretty much like a data center in Google. It's a rack of machines. In this case, a rack of routers. Okay, so rack of these routers. They're interconnected between each other, and they are also offering connections to the customers. and some of them might be connected to other tier 1 ISPs. And these links are to go further up into the backbone, in the hierarchy of the backbone in Sprint's network. And this is internet structure, a network of networks. All right, so internet. So in the very last part of the video, you see that in a real network, the connectivity and what's inside the hub, there could be many routers, switches, some handling external connections, some handling internal connections. Quite messy, but they somehow find a certain order and works and support the operation of the internet. And by the way, Sprint there, I think was merged to T-Mobile. Okay, so T-Mobile started off as a mobile internet provider, but now merging with Sprint, so they now also have access to part of the backbone and also offer mobile access. So what's interesting about internet structure is this. You see that these content network providers, they are actually sitting at the very, very edge. Okay, but in terms of resource, they are probably equally high as the backbone providers. And hey guys, we see that Lucas and August is they are having a discussion there, talking about how many of these tier 1, the major backbone ISPs are. Yeah, thank you guys for the discussion. Yeah, Sprint again. Oh, really? All right. I guess, in the business world, you never say never. Okay. Yeah. So, yeah, you know what? August and Lucas, feel free to also share with us the sources on the Discord. All right, so let's move on. This concludes chapter 1.3, and we move on to chapter 1.4, which talks about how we measure internet performance. Okay, you see that when later on we'll talk about protocols, and these protocols are essentially mechanisms to determine how messages are exchanged. Right? We would definitely like the internet to perform well, and therefore how we judge whether one protocol is better than another is exactly based on these performance metrics. So this video introduces the metrics we'll introduce today. Starting from here, we'll focus our discussion mainly on the packet-switched internet. And 1.4 is to talk about the important metrics we care about designing protocols for it. That includes delay, loss, and something called throughput, which we'll talk about at the very end of 1.4. How do loss and delay occur? Well, let me draw your attention to the example below, that'll be easier. First kind of delay is happening here, in the packet that is going out, being transmitted out. That delay the packet is experiencing is called the transmission delay. That is the time it takes to transmit the packet, and we know how to calculate, don't we? It's packet size divided by the link rate. But there's a second kind of delay experienced by packets here before they get to go out. These are what packets waiting in a queue, waiting for its turn. And how can there be packets waiting in a queue? It actually happens quite often when the incoming rate exceeds the outgoing rate. So you see in the example, A and B sending packets actively together into the router. In case the aggregated arrival rate is higher than the outgoing rate here, then you will see there will be always packet here waiting to be transmitted, and therefore subsequent packets will need to wait up. And that is queuing delay these packets are experiencing. Now the calculation of queuing delay is a lot more challenging than the transmission delay. It really depends on the arrival pattern before a packet comes into the queue. Okay, now if that pattern is reoccurring, predictable, then it will be easier to calculate this. Otherwise, very challenging. Now, that explains packet delays, where they might occur. Packet might get lost as well at the router, and it happens here. Focus on this thing here. It's the packet queue. The size of the packet queue is limited. Okay. By the way, that packet queue is also often referred to as the buffer. Okay, and the buffer space is limited, just like the memory space is limited. The buffer space is just a way of calling the memory reserved, okay, to store these packets. Now, given that the amount is limited, in case congestion persists for a long time, then eventually you run into the situation. There's no longer free buffer space in the queue. In that case, arriving packets will get dropped, and therefore we see packet losses. So you see then what's coming up. We measure delay. That's one of the metrics. We measure also loss. That's the second metric. In fact, later you will hear that there's yet another metric called throughput. Okay, so let's start from the first metric, delay. Okay, so first video kind of dissect how we measure end-to-end delay. There are actually, measure hop-to-hop delay. There are actually 4 components. Now, packet delay. There are 4 components. The first component is the nodal processing delay, but we just call it processing delay. It occurs right here when the packet arrives at the router. Router here checks the bit errors in case there's any, and decides quickly which output link the packet should go out. Next, queuing delay. That's the time the packet waits until it's turn to go out on the output link. So it occurs right here at the buffer space where packet queued up. But the amount of wait depends on the congestion level of the router. Component 3 is the transmission delay, and it's calculated this way. R being the link bandwidth, L being the packet length, and the time to transmit the packet out will be L divided by R. And it's happening right here at the interface between the router and the link. Final component, propagation delay. Provided the length of the physical link and the propagation speed of signals traveling the physical link, we know that the propagation delay is D divided by S. So essentially the time for the packet to traverse the physical link. Be careful, S here is the distance the signal can travel per second. R here is the number of bits the transmitter can push out per second. Although I call S the propagation speed, R the link speed sometime, but there are 2 very different quantities. Yeah, so there are 4 components. Processing delay, normally negligible. Queuing delay, quite complex. Polly will talk about that at the very end of the delay discussion. But you see, at the very end of the video, the transmission delay and propagation delays are computable. Okay, so in the next video, let's try to calculate propagation delay and transmission delay using 2 examples. Right? Now let's go through a couple examples to exercise calculating transmission delay and propagation delay. What you're seeing here is a caravan of 10 cars. Now the way to think of this scenario is this. Think of cars being bits and caravans being a packet. So we have a packet containing 10 bits in a sense. The cars will be propagating at the speed of 100 kilometers per hour over 100 kilometers, reaching the second booth. Toll booth number 1 here takes 12 seconds to service the car. All right. Question here is asking how long until the packet is lined up before the second router. All right, so transmission speed, transmission delay plus the propagation delay. So what is the transmission delay? We have 12 seconds serving per bit, and then there are 10 bits. So the time to push the entire caravan out of the toll booth is 2 minutes. And then the propagation delay is for the car to travel 100 kilometers. So 100 kilometers dividing the propagation speed. So we have 60 minutes here. And so altogether, 62 minutes before the entire caravan to reach the second toll booth. So you see, in this case, transmission speed, very fast. Propagation speed, slow. In the second example, the configuration is slightly different, mainly propagation speed and transmission speed. Propagation speed now goes really fast, but transmission speed much slower. So question here is asking, will the first car arrive at the second toll booth before all the cars are being serviced? Let's see. When will the first car arrive at the second toll booth? So transmission delay, 1 minute. Propagation delay. So we have 100 kilometers, but we're traveling 1,000 kilometers. So we'll be spending 1/10 of an hour propagating, and that's 6 minutes. Together, 7 minutes. So the first car will spend 7 minutes before arriving at the second toll booth. Now, 7 minutes is also the time to service 7 cars for the first toll booth. That means we have 3 cars that are still behind at the first toll booth. So yes, okay. When the first bit arrive at the next router, there could still be bits not yet transmitted out from the previous router. So in this case, where the propagation speed is really fast, transmission rate very low, you had this weird situation. Yeah, so that's 2 examples, calculating propagation delay and transmission delay. Sometimes the propagation delay could be much longer than the transmission delay, and sometimes vice versa. So this next video is almost like summarizing the 4 components, how they can be computed, and talks a little bit more about the queuing delay and how hard it is to estimate. Good. Let's sum up packet delay. So there are 4 components: processing delay, queuing delay, transmission delay, and propagation delay. Transmission delay, very low, typically microseconds. We just ignore the processing delay when we calculate packet delay. Transmission delay, propagation delay, very easy to calculate. L divided by R, this quantity is often significant and especially the case for low speed links. Propagation delay, slightly harder. It varies quite a bit from microseconds to hundreds of milliseconds. So this extreme is for satellite links, for example. We've seen earlier, it could go up to 200 or even more milliseconds. Sometimes the transatlantic or trans-Pacific links, very long optic fibers, could also take up to 100 milliseconds. Now, in the process of calculating packet delay, the hardest component is this, queuing delay. Now, it's very hard to calculate accurately because it depends on the congestion level at the router. Just to give you a sip of how hard it is, let's define again, R being the link bandwidth, L being the packet size. Let's add one more variable, the average arrival rate. So L multiply A is the average bit arrival rate. That is also the incoming traffic rate. R is the outgoing traffic rate. So we could define traffic intensity being LA divided by R. So when that quantity is close to 0, that means incoming rate very low, outgoing rate very high, then no bits really need to wait. So queuing delay very small. And it's depicted here. When LA divided by R is very small, queuing delay also very small. The other extreme is here. When the intensity is greater than 1, that means there are more bits coming in than more bits going out. And when time goes on and on and on, the newly arrival bits will need to wait longer and longer and longer. And it's pretty much here, approaching infinity. Now, when the intensity is between very small to 1, delay is simply growing. And as we will be approaching infinity, you see that the curve grows quickly like that, okay, close to an exponential trend. So hard to estimate queuing delay. In fact, it takes a whole semester for a professor to teach about how one calculates queuing delay. And at the graduate school, there's advanced queuing delay that one can also take to make sure that you do a better job, okay, estimating queuing delay for highly dynamic incoming traffic. All right, so that is delay. This very last video talking about delay is actually showing delay can be measured and measured by this program called traceroute. And oh guys, by the way, pay attention to this video because quiz 6 is coming up and it's just about traceroutes and how you analyze traceroute results. All right, so that was the theory part of the packet delay. One can also find out what is the real internet packet delay by trying out this program, traceroute. Okay, what it does is to measure delay from a source, one hop at a time, all the way to a destination. So this is what I'm drawing here, source to destination, and it's sending 3 packets, one at a time, to reach each of the routers along the way. So router there receiving such a packet would return by sending a reply back to the sender. Now, the sender there can time the interval between the transmission and receiving the reply and gets one estimation of the round trip time between the sender to the router. So it works like this. 3 probes to the first router, 3 round trip time estimation. 3 probes to the second router, 3 round trip time estimations to the second router. And this goes on and on until it reaches the final destination, and then the trace route program stops. The output of the program looks like this. This is an example. Trace routing from Gaia, UMass.edu to Oricom, France. So this is saying first hop router's name is CS-GW at IP address 128.something.something.something. And there are 3 round trip time estimations, 1 and 2 milliseconds respectively. What's a little bit interesting is between hop 7 and 8. There, you see at hop 7, round trip time was about 22 milliseconds, but suddenly to hop 8, the delay is about 100 milliseconds. So that is the transatlantic links connecting from US to Europe. A little bit more interesting is also hop 17 and 18. You see stars, stars, stars. That means the routers are not responding. Okay, and it could be because the probing messages are lost or the replying messages are lost. But it's more likely that the router is turned off replying to these. Routers are on, but the routers turn off replying these probing messages. Well, let's try, sending a trace route ourselves from here. How about that? Let's go over to a terminal and then trace route to say Google. How about that? All right. Good. First hop router. Well, it didn't tell me the name of the router, so chances high that the router doesn't have a name. Okay. Delay reasonable. 10 millisecond, 3 millisecond, and another 3 millisecond. Router 2 here, well, either the probing messages are lost or router turns off the functionality of returning to trace route probes. Now third hop, 30 milliseconds, suddenly much higher. Okay, fifth hop, delay not much higher than the third hop. And you see here, when it's star, 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 it takes longer time. It's because when the traceroute program sends the probing packet, there's a timeout interval. Traceroute will wait until the time exceeds the interval. Then it determines that, hey, the router is probably not going to respond anymore. So forget about the first probe, send the next probe. Next probe waits also some amount of time. Timeout, give up, and then sends the third probe. Okay, good. Finally, we reached www.google.com. But the name is actually quite different. TSA something something. Interesting. And the end-to-end delay, end-to-end round trip delay to www.google.com is about 20 something milliseconds. Now, something that's very odd is here. Hop 8. If you look closer, we do have 3 round trip time estimates. But each time, number A here along the way, the 8th hop, is slightly different. IP address is 101, 49, and 97. So you see here, packets, although going to the same destination, coming from the same source, as they go on the internet, the routes could actually change. Also, you see, hey, the time it takes to reach hop 5, 30 milliseconds, but the time it takes to reach hop 12 is only 20 something seconds. So the load of the internet changes also over time. So sometimes when you are probing to a closer router, could take a longer time because it was busier there. But when the traffic load drops and when you're probing a router that are farther away, you could get a shorter round trip delay. Yeah, very curious. And let's go back to the slide. And it turned out that it's a good time to start the next quiz.
That's quiz 6. All right. So what you're seeing here on the quiz is the output of the exact trace route you see from the slides earlier. Okay, it's the same thing. Okay, probing from UMass to Oricom, France. So in quiz 6, I would like to ask you these questions. Q1 says, hey, how come the 3 delay measurements are not always the same? So we can see for hop 7, right? The 3 probes delays are the same, 22, 22, 22. But there are more often, for example, hop 4, 16, 11, 13. Even for hop 1, 1 millisecond, 1 millisecond, 2 millisecond. So how come the three measurements are not quite the same? What are the reasons? Q2. How come some delay measurements to hop 10 are longer than those to hop 11? So where's 10? 10 is here. 11 here, right? So delay to hop 10. Delay to hop 11. So delay to hop 10, particularly this one. 122 millisecond. This is longer than any of the delays we measure probing to the 11th hop, right? How can this happen? And Q3. Okay, so Q3 is open-ended. So I ask you to estimate the delay between hop 3 and hop 4. So in a way, from here, you see, the round-trip delay to hop 3. From here, you see the round-trip delay to hop 4. Can you estimate the one-way delay from hop 3 to hop 4, given those values? So can you come up with a mechanism estimating the one-way delay from hop 3 to hop 4? And try to use the same mechanism to estimate the one-way delay from hop A to hop 10. So hop A, 3 measurements, hop 10, 3 measurements. Now, in case it doesn't work, then you might want to think maybe a more general, reliable mechanism that will work estimating both delay from hop 3 to 4 and hop 8 to 9. Okay? So let's go to the score here. The quiz appears in channel W3, quiz 6. Again, as I mentioned, for Q1, Q2, it might be straightforward, but Q3 might require a little bit of brainstorming. So gather your teammates. You guys have 7 minutes to discuss and 1 minute to post your answer. Okay? And it's, guys, you know what? It's already 11:07, all right? So why don't we take a break? In the meantime, you guys having a discussion. And so we'll resume and come back to check your solutions at 11, let me see, 7 and 10, 17 minutes. So that will be 24. So that's resume the lecture and come back to check your answers at 11:24. So in a way, in the 17 minutes in between, it's break plus brainstorming time. Okay? So let me start counting. Oh, actually, no, let me do the break audio. Okay, so let's take a break, and you guys do the brainstorming. We'll resume 11:24. Yeah, I guess many of you are still trying to figure out a mechanism and type the solution up. But you know what? We have already several teams coming up with their solutions. So team one, I guess still brainstorming, but it seems that at least for the first two Qs, they felt that the differences across the three measurements are mainly jitter. So the delays, the queuing delay for the 3 rounds of probes might be slightly different. So that's the top reason that the delays are not always constant. Because having some different queuing delays in the system before arriving at the destination, that is just very common. For second one, yeah, so there's a chance that they are taking different routes, as you see in the demo in the video, right? So jitter is so big that the 3 probes for the next hop turned out being shorter than the 3 probes in the previous hops. So it can be that the delays to the previous hops happen to be super long as traffic are very, very busy at the time these probes are taken. But then, of course, routes being different. So you see now, common answer to these, unpredictable delay, queuing jitter, and different paths these probes are taking. Now, I anticipate that you guys have similar answers for Q1 and Q2, all right? So let me just take the answer for Q1, Q2 easy. Q3, however, right, can be a little bit tricky. Yeah. So, so team 1 here having discussion. So there I see August was suggesting that taking the minimum of the 3 measurement and then subtract the minimum from the 2 hops. So that's definitely one way, right? And if you divide it by 2, then you get the one-way delay. And then team 4? Team 4, I think answer down here. No, not yet. Team 4 answer down here. They take the difference of the last measurement. Okay, so there are 3 measurements. They take just the last one. Yeah, that is the latest delay difference. Well, in a way, right? That's another way to estimate the delay between the 2 hops. But this will be the round trip delay though, team 4. Okay, so for one-way delay, you will need to divide it by 2. But that is minor. And let's see what here, team 10. Team 10 says could change due to different internet conditions. They could be because the differences could be because of they follow different paths. The 3 probes to the previous hops, one path. The 3 probes to the next hops, different paths. And the delay is estimated this way. For hop 3 to hop 4, oh, they take the average. Okay, of course, this is one way. I think similarly for hop 8 to 9. Yeah, because the outcome here is a negative value. I guess what they meant here is, so in case it's negative, that means that the delays to these 2 hops are probably very, very close, right? So they just say that delay very close, less than 1 millisecond. Okay, so team 10, very complete, the answers. Team 11. So team 11 actually take the average of the min and the max. Interesting. Yeah, so you take the min and max and average the min max. That's interesting idea. So that is certainly one way, I have to say. It's very interesting. All right. Okay, so I guess team 7 is taking the same approach as team 10, right? So this after this, it's almost average. So this is again, it's negative value, so you guys just say that the delay is just very small. Average. So team 11 is also taking average of the 3 measurements. Yeah, so I guess more teams are taking average, right? That seems to be one very straightforward, the first idea you can come up with. All right, Lucas, team 2. Very interesting. I understand. Yeah, if it's a negative value, it's not sensible. Yeah, so people who are more careful about seeing such a result, then will think again. Yeah, so maybe just take the average and subtract them is not the best way to do it, right? And this can be improved by weighting the average, for example. Interesting. So one can weigh the original hops higher than the O1. Very interesting idea. So let's see the solution here. Between hop 3 and 4, the situation is relatively simple. I agree. Subtract the mean. Could improve by weighting, yes. The last resort effort could also be to retrace these 2 routes interleaved. Oh, interesting. Interesting. So in addition to trying to weigh the hops measurements differently, this is a very interesting solution. So instead of taking measurements for hop A consecutively and hop 9 consecutively, they try to interleave. Therefore, the differences between the first measurement of hop A and first measurement of hop 9, because they're closer, that makes more sense to just subtract the 2 of them. Interesting. So the deviation, so get the 2 measurements when the deviation is not so big. So this is a mechanism that is not just to calculate given the measurement, but to change how to do the measurement. Very thoughtful, Lucas, team 2. Nice. All right, I guess, yeah, so to estimate the delay, it could be a little bit challenging, right? Very open-ended. Many of the teams are typing their solutions. That's great, guys. Keep going. There was a question here. Ryan was asking, did you ever go over what exactly the peering links did? Are they for ISPs to see what's inside other ISPs so they could know where to send data? They are mainly just to have a connectivity to the peers, to the peering ISPs. So that's a lot of times the entry point or the exit point of data from the peering ISPs. All right, good. Oh, we have more teams typing up their solutions. Hey guys, great job there, thinking about having a good solution. I understand it's a little bit challenging and could be taking more time, so it's okay. But you know what? The lectures must go on, all right? So what we have so far is one important measurement, delay. Nowadays, delay is the most important because we don't see much loss anymore these days. Okay, and loss is the second metric, which is very straightforward. Packet loss is a lot more straightforward. You see, it's because the queue is finite in capacity. So in case a packet arrives when the queue there in the router is already full,
So you see this full packet here, will need to be dropped. That's why we see packet losses. Now, what we haven't discussed is this, the lost packets. To some application, it's actually okay to have packet losses. If it happened, let it happen. So we will not try to retransmit the packet at all. But in some cases, for some applications, users are expecting the messages arrive fully intact. Then we might need to retransmit. Now, as to which entity in the internet to try to do the retransmission, it's really up to the design. So in some cases, we might see the previous routers doing the retransmission. But in most of the cases, we see the original source, the source end system is doing the retransmission.
All right, so very simple. The last metric is called throughput. Okay, so we know about bandwidth. That is to account number of bits we can send per time unit. Oops. Guys, are you still hearing me? Guys, are you still hearing me? Oh, interesting. Guys. All right, great, great. Good to know that you're hearing me. There's something going on here locally. Hope that I can keep the stream going. Well, okay. Okay, great, great. So I guess it's just I know. Yeah, cuz so my computer here is funny. I guess some of the IO ports are having some sort of conflicts. Therefore, the camera is on and off, the microphone is on and off. So let's keep going and see how far we can go. All right. So the next thing is called the throughput, and we know that to measure the link bandwidth. Yeah, it is. It is. And it could be a network problem, but it could also be the device, the IO, within my computer. Okay, I'll do some checkup after the session today. So to measure a link bandwidth, we account number of bits we can send over 1 unit time. Okay, so that's link bandwidth. Throughput, the unit is the same. Also, number of bits per unit time, but it's to count the number of bits we can send from end to end, from the source to the
is the third metric. And it measures this thing, the rate of transmitting data all the way from the sender to the receiver, from one end to the other end. And the speed of data is going through the entire channel, entire pipeline. Now, there are two ways of quantifying throughput. One is called the instantaneous throughput, the other average throughput. Now, the units are both bits per second. Okay. But instantaneous throughput is more that you're measuring the throughput at a particular point in time. You will see that if you measure instantaneous throughput, it will fluctuate down the situation of the source and destination. For a longer period of time, then you see that the average throughput is more or less stable. Okay, so the throughput here we're talking about and discussed throughout the rest of the slides will be more the steady state behavior, the stable average throughput, just to clarify. Now let me elaborate the example a little bit more. This is the sender, this is the receiver. The sender is essentially a file server hosting big files here over to the client requesting the file. And so we're talking about just, okay, not the request part. And connecting the server and the client, we have one link, one switch, and another link. So it's a two-hop network.
So guys, are we back online? So those are still in the YouTube session. Can you let me know? Ah, all right, yay! You know what? Hey, better than not fixing it. So then we can go on and try to finish the last metric. Did you guys hear the loss? The video about loss being straightforward? Very good. Thank you. Thank you, guys. So what about the last metric, throughput? Yay, we're back. Yeah, what about the last metric? Have you guys heard throughput? No, not yet. But you guys got lost, right? I see. So the last video is also laggy. So why don't we just go over them again? Because this semester we are slightly ahead of time. So we do have some spare time to accommodate glitches like this. Okay, so reset, we're back. So delay is the first metric. So we went through quiz 6, exercising analyzing delays. There are two more metrics. Yeah, so there are two more metrics, loss and throughput. Loss is straightforward, so very short, within a minute.
Packet loss is a lot more straightforward. You see, it's because the queue is finite in capacity. So in case a packet arrives when the queue there in the router is already full. So you see this full packet here, will need to be dropped. That's why we see packet losses. Now, what we haven't discussed is this, the lost packets. To some application, it's actually okay to have packet losses. If it happened, let it happen. So we will not try to retransmit the packet at all. But in some cases, for some applications, users are expecting the messages arrive fully intact. Then we might need to retransmit. Now, as to which entity in the internet to try to do the retransmission, it's really up to the design. So in some cases, we might see the previous routers doing the retransmission. But in most of the cases, we see the original source, the source end system is doing the retransmission.
Yeah, so you see that loss is straightforward, right? It's measured by the loss rate, and it's caused by buffer overflow. The last metric is called throughput. The unit of throughput is number of bits per unit time. Okay, and this is very similar to the link bandwidth that you've been seeing before. The number of bits a link can transmit per unit time, per second, for example. But throughput is not like bandwidth. Bandwidth is to account the amount of traffic you can push within a link from a hop to another hop. But throughput is to account the number of bits you can pass within a unit time from a user to another, from one end to another end. So this is end-to-end bandwidth in a way. So throughput. Now this is the video to explain the whole thing.
Throughput is the third metric, and it measures this thing, the rate of transmitting data all the way from the sender to the receiver, from one end to the other end, and the speed of data is going through the entire channel, entire pipeline. Now, there are two ways of quantifying throughput. One is called the instantaneous throughput, the other, average throughput. Now, the units are both bits per second. Okay. But instantaneous throughput is more that you're measuring the throughput at a particular point in time. You will see that if you measure instantaneous throughput, it will fluctuate depending on the situation of the channel between the source and destination. But if you observe over a longer period of time, then you see that the average throughput is more or less stable. Okay, so the throughput here we're talking about and discussed throughout the rest of the sites will be more the steady state behavior, the stable average throughput, just to clarify. Now let me elaborate the example a little bit more. This is the sender, this is the receiver. The sender is essentially a file server hosting big files here. Let's say the file of F bits is being sent over to the client requesting the file. And so we're talking about just the file download, okay, not the request part. And connecting the server and the client, we have one link, one switch, and another link. So it's a two-hop network. And the link capacity for the link directly adjacent to the server is RS, and S here indicates it's the link to the server. And this guy here has the link capacity of RC, and C indicates this is the link rate for the link connecting to the client. Now, let's consider, okay, such a data pipeline as a fluid pipeline, water pipeline. Then you see, I'm drawing, okay, the pipeline's width, the diameter, based on the link capacity, RS. So RC here, let's assume it's larger, then you see a bigger pipe versus RS, smaller pipe. And you can also think about the server here being a what? Okay, a water tank, dumping waters, dumping fluid into the entire pipeline here. Now, it might be a little bit easier for you to imagine, right? What is going to be the pipeline's throughput if you consider how the fluids will be arriving at the receiver effectively? Would it be RC or RS? Well, it's probably not that hard, isn't it? Because the intuition tells you that, hey, this guy here, RS being smaller, will limit the amount of fluid that can travel through. Okay, even though RC is bigger, yeah, the amount of water that will go through here effectively to the receiver is still RS. If it's the other way around, RS being larger than RC, yeah, there could be a lot more water coming in, okay, overall carrying RS throughput, but this guy here being thinner is going to limit the rate of the fluids travel through. So in the end, at the receiver, okay, RC is going to be the throughput. And this guy here and this guy here, the link on the end-to-end path with the smallest bandwidth is going to constrain the eventual throughput. Okay, so throughput here oftentimes is being called the end-to-end throughput to indicate that it's the rate of data being sent from the source, one end, to receiver, the other end. Well, after drawing the data network to a fluid network, you see that it's very intuitive how you derive the throughput from one end to another end. And those scenarios are very straightforward, just two links. Let's consider a case that's a little bit more like the internet, okay? Deriving the throughput for an internet-like scenario. So you see here, we have servers and clients, okay? Data will be going from the servers down to the clients through the backbone, the internet backbone. So for each connection end-to-end, we'll be going through how many links? 1, 2, and 3. So we'll be taking the bottleneck link bandwidth as the throughput. So we'll be trying to get the minimum of the 3 segments. Okay, RC is this guy, RS is this guy, clear. The middle segment, well, if there are 10 links in parallel, then this middle link here, capacity R, will need to be divided by 10, as I'm assuming the 10 connections are fairly sharing the entire capacity. So the throughput to be formulated is this, minimum of RCRS and R over 10. In practice, however, okay, nowadays on the internet, usually it's either RS or RC being the bottleneck. You see, this is an N system, this is an N system. We subscribe access to the internet through some ISP. So this, usually the rate is low. Just like this, the application service provider, they are also subscribing to their ISP. This is also low. As opposed to the big R here in the middle of the internet, in the backbone, those are usually large. It's just that nowadays, there are a lot more connections sharing the big R. Okay, most of the time, RC, RS are the bottlenecks. But occasionally, you might also see when network is really congested, R is not quite enough to allow all the connections demanding services.
All right, so throughput, that is the last metric. And how appropriate that we get to experience delay and loss in the middle of lecturing delay and loss. And you know what? Hey, it's okay. We are actually done with chapter 1.4. So slightly ahead, let's enter chapter 1.5. Now, this is the third topic set that is not technical at all. So all we talk about is, hey, protocols in layers. So the first video is to let you know, okay, in internet service model, why it's necessary to talk about, to organize all these protocols into layers or having some sort of organization. Okay.
Now let's recall all the terms we've referred to since the beginning. Right? We've seen hosts and systems. They're essentially the machines composing the edge of the internet. And then the core of the internet, right? The other one at the center of the internet being a mesh of interconnected routers. And then connecting the edge and the core, we do have these access networks or access links that operates different kinds of physical media running different kinds of modulation mechanisms. Yeah, access network. So these nuts and bolts compose and form the physical infrastructure of the internet. So this is more the hardware side of the internet. But we also talk about that, hey, hardware is not the only thing that makes the internet work magic today. A lot of times we rely on these applications in order to see a page that we are looking information from. Okay, so applications such as World Wide Web email, and these applications a lot of times, right, it's implemented in a way that there's some part of the application running on one physical entity and then another part running on another physical entity. So if you recall for World Wide Web, there's the client side on the client machine, and then there's the server, the web server running on the web server machine. Okay? And these are client and server side will need to communicate based on a specific rule. Okay, and so those rule forms a protocol. So there's also a protocol for the World Wide Web. Okay, so this is one example of the software on the internet, and there are a lot of these softwares. Okay, an application is just one kind of software, right? So in terms of software, okay, there are a lot more to talk about, a lot more pieces. In fact, the hardware part, and this is a very simplified view, okay, there are also a lot of other hardware pieces as well. In fact, to talk about a complex system like this, we do have a major question to begin with. Okay, is there a way, a hope to organize these pieces so that it's a little bit easier to teach or a little bit easier to discuss? Okay, not just between the senior network engineers, but also for the incoming network engineers, and how the senior ones teach the junior ones. Okay.
Yeah, so very simple. We've got to organize all these pieces for such a complex system. Otherwise, it's just very hard to enter this field. All right. And next video is to give you an analogy that is drawn from air travel. you will see that in air travel, there are also many, many pieces, and these pieces are organized in a layered way. Okay, so this video, a little bit long, about 6 minutes, but after that, you might be convinced a little bit more that for such a complex system as internet, we might need structures as layered as the air travel. Hopefully with the air travel example you see, in a large complex, sorry, glitches again, wrong video. Now this is the analogy of air travel. Let me try to use an analogy, air travel here, to show you that it's kind of important to have some sort of organization, some sort of architecture, okay, to make sure a complex system will work seamlessly. And you will see also air travel and internet. Okay. Air travel to communicate people, internet to communicate data. They're somewhat similar, and therefore the architecture used by air travel is similar to the architecture used by the internet. Yeah, by architecture here, I meant the service model, the way the service operates. Good. Now, recall your experience traveling through air. First thing you do, purchase the ticket that guarantees you a seat. At the day of travel, you walk up to the counter, you present your passport and the ticket number. They will allow you to check in your bag and give you the boarding pass. With that, you go to the gate and they let you into the plane. And then the pilot will be negotiating with the traffic control of the departure airport and decide which runway and at what time the plane can take off. And then for a long time, you're just sitting in the cabin and try to get some sleep. But the pilot is busy doing this, okay, routing the airplane. Okay, so as the plane crossing border of some air control, communications will go on again and making sure that the planes traveling the air, the space, will not collide to each other. And hopefully everything is fine at the arriving airport. Again, pilot talks to the traffic control and find out the runway and the time to land. When the gate is connected and open, we may now leave the plane. Most of us go to the baggage claim to pick up our bag and exit the airport. So it looks like it's a series of steps. Very simple. But if you think about it a little bit more, right? Purchasing the ticket is important so that it guarantees you a ticket. So that when you go to the counter, when you're trying to check in your bag, they recognize you, right? And the base of the recognition is on the ticket number, okay? Acquired here and checked here. And in return, you get a bag number, which is used again here. You get also what? A C number, which is used again here. So there are still some communication that needs to be done, for example, between the steps, in between these two steps. Okay? So this component here, more closely related to this component. This component here is also more closely related to this component. And this component also connected and related to this component, even though this is at the departure airport, and this is at the arrival airport. Okay. So you see that there are components that are related, and there are some base in order to communicate between the staff members here and the staff members here. Okay, the mechanism here and the mechanism here. But you see also, for example, baggage check here. Well, it has less to do with the pilot communicating with the central control. Okay, you see also a little bit, right? This is a little bit more like the internet core. The functionality is quite different, but these are a little bit more like the edge of the internet, where you're trying to track data. Here we're trying to track passengers and the belonging of the passengers. Okay. And so that it's probably not that hard to see. There's a architecture there, okay, and it's kind of laid out in layers like this, right? This is communication to traffic control, but at the end, communication to air travel on the other end. Communication of air travel, but from region to region to region to another region's traffic control office. Okay, so to regional office, it's just to make sure that the height and the orientation of the travel is correct. Now these involves also runway. So you see there's slight differences between these two layers. Now these three, okay, are more handling the passengers and baggages, not handling the plane per se. Okay, so which gate
we get in and which gate we're coming out. So your families and members will know where to go to pick you up, for example, to welcome you back, for example. And baggage here, the number is important. At the destination, you also want to know which station is for the baggage claim. There are usually multiple of them, right? So it's also based on the plane number, the flight number. Similarly, ticketing. Sometimes you need to delay travel, right? So you need to call the ticket office again to try to change the day or change the class, okay? And the reference is always, for example, the ticket number, okay? So for communication, you need certain important IDs, important information there, okay? To communicate within a layer, okay? The claim ticket there for the bag is so that you can pick things up on the other end. But there are also certain numbers. For example, ticket number connects to a bag number. Ticket number also connect to a C number here. Okay, so certain pieces of information might be added there, either to allow communication within the same layer from local side to remote side, or information to allow components across layers on one side to try to relate to each other. Okay, so you see, air travel is a complex system. If any step goes wrong, it could end up being a disaster. Okay, needs to be well structured to make sure also that it's efficient. So there are layers. Okay, each layer implements a particular function. Okay, a particular subservice. Okay, and so there'll be some internal actions, but they will also depend on services or functions provided by the neighboring layers. Okay, from the layers below. Okay. Or they might also need to provide supports to layers above.
All right, so layered. So essentially, lots of communication within each layer, but it will communicate in its own way. That's very different from the communication in another layer. But a higher layer usually depends on also service provided by the layer, one level lower. But the one level lower service provided by the service even one more level lower. So it's horizontally connected and also vertically connected. It's a very interesting and special way of structuring, organizing complex systems. And guys, you know what? This is all the time we have. Okay. Next Tuesday, we'll start by talking about what is the benefit of talking about internet or organizing these protocols or pieces of the internet in this layered way. Okay. With that said, if you have questions, feel free to post on YouTube chat or on the score. And those who don't, I say goodbye. Sorry about the glitches. Glad that we're back. At least we finished chapter 1.4. Okay. And the remaining part of chapter 1.5 is very little. So next week we'll be able to enter chapter 2. Okay, smoothie. So that's all. Bye. Goodbye.
Alright guys, I'm gonna end the stream now.